for our first example problem, let's consider a hydrogen atom. So we have a hydrogen atom. And you know what a hydrogen atom is like. It's a proton and an electron. Okay, now the electron is not really orbiting around like a planet around the proton. It's really a lot more complicated than that. It turns out that the electron actually, any object, subatomic particle that's moving has a wave function, and so the electron actually exists as a standing wave simultaneously all the way around there. That's beyond the level of this class to really explain that in detail. That'd be physics 3. It turns out the Bohr model of the atom, which approximates an atom as an electron going around in an orbit of some sort, quantized orbits, only certain orbits are possible, that this is and again, that those orbits come from the standing waves. But if you go to the mathematics of how that works, it comes up within a fraction of a percent of what's really happening with the hydrogen atom. And so that makes the Bohr model a very, very good approximation of what's really happening. And so that's going to be something that we're going to approximate here. And so we're going to pretend that the hydrogen atom is a proton, and the proton has an electron out here, and the electron is orbiting at a distance that we're going to call R0. R0 is the Bohr radius, so that's going to be 5.29 times 10 to the minus 11 meters. So it turns out that while this is not exactly what a hydrogen atom is like, the mathematics of this works really darn good. And so if we think about it, we say, well, wait a minute, what kind of forces are involved? Because if this electron is going around, there's got to be a centripetal force. So there's got to be some kind of centripetal force in here. What can be causing that centripetal force? Well, you remember from physics 1, you got a planet and a moon. So you got a planet and a moon. So the force due to gravity is going to be capital G, the universal gravitational constant, m1, m2 over r squared. So we could actually figure this out. We could say, well, the force due to gravity would be the gravitational constant. That's going to be 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Okay, we multiply by the mass of a proton. Mass of a proton is 1.67 times 10 to the minus 27 kilograms. Then we multiply by the mass of the electron. That's going to be 9.11 times 10 to the minus 31 kilograms. Then we divide by that Bohr radius, 5.29 times 10 to the minus 11 meters squared. And so the force due to gravity in a hydrogen atom between the proton and the electron, it turns out to be 3.6 times 10 to the minus 47 newtons. Okay. Now, technically, we'd probably put a minus sign in there to indicate that it's an attractive force. Now, for the same situation, though, we also know there's electrical forces in here. We get a proton, we have an electron. So we know there's an electrical force. That's given by Coulomb's law. K sub E, Q1, Q2 over R squared. So if I want to find that electrical force, then K sub E, which is 8.99 times 10 to the 9th Newton meter squared per kilogram squared, okay, times the 1.602 times 10 to the minus 19 coulombs. Well, that's the force that's the charge on a proton. Charge on an electron is exactly the same, except it's negative. and then divide by the 5.29 times 10 to the 11 meters squared. And so we find that the electrical force is going to be minus 8.24 times 10 to the minus 8 newtons. Okay. The electrical force we just found was minus 8.24 times 10 to the minus 8 newtons. The gravitational force was 3.6 times 10 to the minus 47 newtons. Look at that. That's 39 orders of magnitude. The electrical force is more than 10 to the 39 times stronger than the gravitational force. Now let that sink in. You have never seen a 10 to the 39 of anything. 10 to the 39 is actually a number that is bigger than the number of atoms that make up the solar system. That's a phenomenal number. This is huge. I mean, there's nothing in your experience that is 10 to 39 times bigger than anything else. And so that makes this enormous difference in strength between the electric force and the gravitational force. In fact, no other force is this much different from anything else. There's only four forces. There's only four forces that we know about in nature. There is the electromagnetic force, and we're going to find out more this semester relating magnetism and electricity. They turn out to be different aspects of the same force. There's the gravitational force. There's two other forces that exist. There's something called the strong force, and there's something called the weak force. Now, the strong force is really, only 100 or 1,000 times stronger than the weak force. The weak force is a little bit stronger, 100 or so times than the electromagnetic force. The electromagnetic force is 10 to the 39 times stronger than gravitational force. Gravitational force is by far the baby force of all of these. Not even close. It is unbelievably weak compared to the rest of them. Now, these two forces you don't know much about in normal experience because they're very, very short range forces. They have a range that's roughly about the size of the nucleus of an atom, so we often refer to them as nuclear forces, though that's not entirely correct, particularly with weak force. The electromagnetic force, we know a little bit, you experience a little bit more. Now, really, that's the force that you, other than gravity, that you normally interact with. Like if you fall down and go splat on the ground, the force between you and the ground is really the electromagnetic force. It's the electrons of the ground repelling the electrons of your body as you go whacking into the ground. Okay, and so if a baseball bat hits a baseball, it's the electrons in the bat repelling the electrons in the ball that's the force between the two. So that's the main force that you really interact with an awful lot. Gravitational force is out there. Of course, that's why you fall down and go splat in the first place. And it keeps the moon orbiting the Earth, the sun or the Earth orbiting sun orbiting the center of the galaxy, and so forth. It's what causes galaxies to collide. Andromeda galaxy is on collision course with the Milky Way. So all of these things relate with gravitational force. But the question is, if it's so weak, why on the big scale does it matter so much? And the reason is severalfold. The strong force and weak force are so short range that at a macroscopic scale, you don't see them operating. The other thing is they're both attractive and repulsive, so they tend to cancel each other out on a large scale. The electromagnetic force is both attractive and repulsive. Turns out there's essentially equal numbers of positive and negative charges in the universe, and they get attracted towards each other, and they tend to cancel out the forces. Earth has a lot of protons, has a lot of electrons, but it has the same number of protons and electrons, so Earth doesn't really have an electric charge to it to speak of, and so you don't normally feel that electric charge. Gravity is the weird one here. Once again, gravity is only attractive. In science fiction, there is anti-gravity. In physics and reality, there is no anti-gravity. And so gravitational force is only attractive. And so that's why even though it's incredibly weak, if you add up enough stuff, all those atoms, each one of those atoms has a little bit of gravitational force, and so it eventually dominates. But that's kind of an oddity right there. Gravity does not conform to any of the other forces. And this is actually a fascinating aspect of physics, which is beyond the level of this class. But I thought I'd just bring it up because it is kind of an interesting sort of thing.